There are many ways to find experimental values for gravity. Some involve masses and pulleys, others involve large buckets of water or even atomic clocks. In this activity, we use a pendulum, a razor blade, and a ball to find an approximate value for gravity. A ball attached to a string swings toward a razor blade. The string is cut and the ball falls, describing a parabolic path. In this presentation, I am going to describe the physics involved in this experiment, develop a strategy for finding gravity, and go through the steps of the experiment, data collection, and computation. The ball attached to a string is lifted vertically some distance h. Initially, the only forces acting on the ball are gravity and the normal force, or here the tension in the string. According to Newton's first law, the ball is not moving, therefore both forces are equal and opposite. When we lift the ball, we apply a force equal to the normal force over a distance. This is the definition of work, force multiplied by distance. According to the work-energy theorem, the work we did on the ball is now potential energy. This means that the ball, being where it is, has some energy equal to the gravitational force times the distance, h. By the law of conservation of energy, the sum of the potential and kinetic energies in a system is equal to the total energy present in the system. If there is no kinetic energy, if the ball is not moving, all the energy is potential energy. This is our starting point. If there is no potential energy left, once we drop the ball, all the energy is kinetic. This is our finish line. Now we have a way to compute the initial velocity. We know that when the string is cut by the razor blade, all the energy is kinetic. Kinetic energy is given by 1/2 of m times v squared. So, our initial velocity, perpendicular to the x-axis and tangential to the path of the pendulum, is equal to the square root of 2gh. Now that we have a way to predict the initial velocity from the height at which we drop the ball, we can turn our attention to the motion of the ball once the string is cut. According to the superposition principle, anything that happens in one dimension has influence only in this dimension. In the x direction, there are no force present, therefore no change in velocity. In the y direction, the only force present is gravity. We can derive this using calculus, or we can start the data collection and analyze it. With this solid math at our disposal and the data we are about to collect, we can find an experimental value for gravity. So let's drop this ball and see if we can have a good set of data. Not this one. Not this one either. Nope. Okay, well, I guess that this one will have to do. One of the reasons to do this experiment using video is that it is quite difficult to obtain a nice parabolic curve. The string can be too weak and break before reaching the blade, or the ball may be too light and some of the kinetic energy goes up instead of horizontally. So now all we have to do is collect the data for time and the x and y axis. Here I am using a video editing software called Vegas to go frame by frame, but there exist many free software applications that allow to do the same. We enter the data in a spreadsheet, plot the graph x of t and obtain a trend line. All that is left to do is plug the values in our equation. For h equal 25 centimeters and x over t equal 2.14 meters per second, we obtain a value of 9.12 meters per second squared for gravity, quite close to the actual value of 9.81. This activity based on the use of video allowed us to cover a lot of material, all integrated in one experiment: forces, work, energy, superposition principle, kinematics and projectile motion, data collection, graphing, and linear regression. In addition, video was used as a data collection tool, as a means to present the experiment, and as a presentation tool for the results. It also helped develop digital skills, such as the use of spreadsheets. Still, the use of video is not limited to this. Now that we have the data, why not use it? Using the same thinking and tools, I did this animation of a ball going up and down a well a long time ago. Creating animations depicting how things behave in the real world could be an incentive to students who may find an interest to work through the process and apply their new knowledge for creative endeavors.